Okay, welcome to part 2 of day 3. It's wave characteristics. We are going to talk about things in phase. It's the particle or point's position and motion. And if we're talking about them in phase, the points with the same displacement moving in the same direction, so two crests or two troughs. If they're opposite phase, they're points with the same magnitude of displacement but in opposite direction, so a crest and a trough. If they're out of phase, then these phase differences are described using an angle, and so you'll see them shifted one way or another. Frequency, which is abbreviated with an F, is the number of waves passing a given point per unit time, and it can be expressed as waves per second, vibrations per second, cycles per second, or the SI unit, which is going to be hertz, which we write as 1 cycle per second. Again, that's 1/s, or s to the minus 1, which just is another way of stating that. And there's a cute little joke. Okay. The period, which we also have dealt with before, we abbreviate it with a capital T, which is the tau. Given the time required for one wave to pass a given point, and so that would be time, so that's seconds. And the period and frequency are inversely, are related through their inverses, so they're reciprocals of each other. Waves per second in the inverse of seconds per wave, which just makes sense. The wavelength is going to be how long the wave is, of course, and its unit is meters. And we measure it either from trough to trough, crest to crest, or any point to the same point in another that is in phase. The wave's speed or velocity is the rate of change in position, and so the formula for that is velocity is equal to frequency times wavelength, and this is wave through a medium, and it depends on the type of classification, electromagnetic or mechanical, the nature of the medium, such as glass, water, air, vacuum. And this is how we get the separation of the colors of light, like through a prism or something, because each color of light has a different frequency and wavelength, and therefore it's going to be affected by the change in media a little bit differently. The amplitude is going to be the maximum displacement from the equilibrium position, and it can be up or down. As you remember, we used the sign before when we showed it, and it's in meters. Okay, we're going to do a practice problem from page 257, which is just going to ask us to do some calculation. And then if you follow on further down that page, you'll see that there's also some more practice questions that we'll do in class, or you can do at home. So the question out of the book says that the piano string tuned to middle C vibrates with a frequency of 264 hertz. So the frequency is equal to 264 hertz. Assuming the speed of sound in air is 343 meters per second, so there's our velocity, 343 meters per second. Find the wavelength of the sound waves produced by the strings. We want to look for the sound wave. Well, we just had the formula, which is velocity is frequency times wavelength. So I'm just going to plug in the numbers that I know. So I have 343 meters per second is equal to 264 hertz times my wavelength. And if I solve for my wavelength, I end up with 1.30 meters. So again, knowing what the variable is for each of the amounts given is really going to help you know where to put in your numbers. So try a couple on your own. We'll talk about it more in class. And if you have any questions, make sure you bring them to me. Have a great day, and I'll see you soon.